More than 230 million years ago, the Earth was an unrecognizable world. The continents were joined into a single supercontinent, Pangaea, an immense landmass surrounded by the Panthalassa Ocean, where deserts stretched for thousands of kilometers and the seasons were extreme. In this setting, the planet was slowly recovering from the worst extinction in its history, the Permian-Triassic, which had wiped out 90% of marine species and 70% of terrestrial ones. The decimated biosphere offered an empty canvas where new forms of life began experimenting with survival. The first dinosaurs emerged in this hostile world in what is now South America. There, on the humid plains of present-day Argentina, Eoraptor, Herrerasaurus, and Styracosaurus walked, the pioneers of a new era. They were small, agile creatures, barely larger than a big dog. However, their success lay not in brute strength, but in a combination of traits that would allow them to endure for more than 160 million years. Upright posture, speed, efficient lungs, and a biology prepared to withstand the climatic instability of the Triassic. The Eoraptor lunensis, whose name means dawn thief, is considered one of the oldest known dinosaurs. Its remains were found in the Valley of the Moon, in the province of San Juan, Argentina. It was just over 1 meter long and weighed about 10 kilograms. Its irregular dentition, composed of some curved carnivorous-like teeth and others straight like those of an omnivore, reveals that it was at an intermediate point in evolution, not yet specialized but adaptable. Its pelvic structure and long hind limbs allowed it to move quickly on 2 legs, a trait that would be crucial in the later evolution of theropods. Almost simultaneously, another Triassic inhabitant roamed the same lands, Herrerasaurus ishigualastensis, up to 6 meters long. It was a more advanced hunter with serrated teeth, curved claws, and a powerful jaw. Its skeleton shows a surprising anatomical sophistication for its age. Flexible joints, a rigid tail for balance, and muscles designed for active hunting. In many ways, it was the first truly dinosaur predator. The Triassic climate fluctuated violently between wet and arid seasons. In some regions, torrential rains turned valleys into mudflats. In others, the heat cracked the land and dried up rivers. Life survived on the edge of collapse. Primitive dinosaurs shared their environment with other reptiles such as crocodilomorphs, ancestors of crocodiles, and synapsids, mammal-like reptiles that dominated before the Permian cataclysm. But those ancient rulers of the planet were already in decline. Their slow metabolism and sprawling postures made them clumsy under the new environmental conditions. Dinosaurs, with their legs under the body and upright gait, had a crucial evolutionary advantage. In the ecosystems of that time, every niche was contested. Primitive herbivores such as Lesothosaurus and Plateosaurus fed on ferns and conifers, while small predators hunted insects, reptiles, and defenseless young. The competition was fierce, but the rules were changing. Volcanic eruptions released carbon dioxide into the atmosphere, oxygen was scarce, and global temperatures were rising. Yet in this adversity, dinosaurs thrived. Their respiratory system, possibly similar to that of modern birds, allowed them to make better use of the thin air. The initial success of these animals was neither immediate nor absolute. For millions of years, they coexisted with a great diversity of species that competed for dominion over the Earth. Rauisuchians, enormous quadrupedal predators related to crocodiles, seemed destined to rule the Triassic. But their reliance on environmental heat and limited adaptability doomed them when the planet began to cool. Dinosaurs, more resilient and efficient, slowly took their place. The landscape was a mosaic of contrasts. Forests of conifers and cycads covered the wet areas, while vast deserts of red sand stretched toward the tropics. Rivers carried sediments that millions of years later would preserve the fossilized bones of these pioneers. In the twilight of the Triassic, small groups of Eoraptor hunted insects under the shade of tree ferns, while a Herrerasaurus watched from above, ready to pounce on any unsuspecting prey. The social structure of these early dinosaurs remains a mystery. There is no clear evidence of group behavior, but some fossil concentrations suggest they may have moved in small bands or gathered around water sources. Their success, more than in cooperation, relied on individual efficiency. The instinct for survival, agility, and ability to adapt to different diets allowed them to thrive while other lineages went extinct. The fossil record also shows how, from the very beginning, dinosaurs began to diversify. Some adopted strictly herbivorous diets, developing long necks and massive bodies to reach the tops of trees. Others specialized in fast hunting, honing their claws and teeth. This evolutionary radiation was slow but steady, marking the beginning of the split between the major groups that would dominate the Mesozoic. Meanwhile, the planet continued to transform. Pangaea began to fracture due to tectonic activity, opening cracks that would later form the Atlantic and Indian Oceans. Ocean currents altered climates, and new species appeared with each cycle of adaptation and extinction. In the shadows of the Triassic, unknowingly, dinosaurs were preparing for their ultimate rise. With each generation, mutations accumulated, favoring resilience, speed, and instinctive intelligence. Predators became more agile, herbivores larger and more resilient. It was the prelude to a dominance that would span the entire Earth for over 160 million years. And although they were still just one among many groups of reptiles, their fate was already sealed by natural selection. The arid wind of the Triassic blew over the bones of the ancient masters of the planet, the synapsids that had disappeared. In their place, a new lineage rose, still small but unstoppable. Dinosaurs would not only survive but forever transform the history of life on Earth. And on the horizon of that uncertain era, time was preparing the next step, the great division that would separate dinosaurs into two distinct evolutionary paths and define the anatomy of power throughout the Mesozoic. The Great Evolutionary Division, Saurischia versus Ornithischians. The history of dinosaurs, like any great natural epic, is not defined by a single moment, but by a branching. In the middle of the Triassic, about 225 million years ago, when the first lineages were beginning to consolidate, a silent division occurred, an anatomical split that would forever mark the course of their evolution. From a common reptilian origin emerged two distinct branches, the Saurischia, with hips similar to modern reptiles, and the Ornithischians, with hips resembling those of birds. That seemingly trivial bone difference would end up determining who would be the most fearsome predators and who would become the dominant herbivores of the future. The key feature lay in the pelvis. In Saurischia, the pubis pointed forward, as in primitive reptiles. In Ornithischians, however, this bone rotated backward, parallel to the ischium, creating a wider abdominal cavity ideal for prolonged digestion of plants. This simple anatomical alteration gave rise to two opposing evolutionary strategies: mobility and attack versus defense and endurance. What began as a structural variation turned into a design war that would last for more than 160 million years. Saurischia, literally lizard-hipped, further split into two major groups, theropods and sauropodomorphs. The former evolved into bipedal carnivores, the ancestors of Allosaurus, Spinosaurus, and the legendary Tyrannosaurus rex, while the latter evolved into giant long-necked herbivores like Diplodocus and Brachiosaurus. Their body architecture was designed for dominance, powerful muscles, lightweight skeletons, and efficient respiration that would later give rise to an unexpected lineage, birds. Ornithischians, or bird-hipped, followed a very different path. They were primarily herbivorous, many small at first, but increasingly specialized in collective defense and adaptation to various environments. From their lineage would emerge stegosaurs with dorsal plates, ankylosaurs covered in bony armor, ceratopsians with large horns, and hadrosaurs with duck-like beaks. In them, anatomical innovation was not speed but cooperation and behavioral sophistication. The division between the two groups did not happen suddenly. For millions of years, fossils show intermediate species that share traits of both lineages. However, environmental pressure, composed of dry climate, scarcity of prey, and competition between carnivores and herbivores, pushed specialization. On a planet still unified by Pangaea, where deserts stretched from the equator to the poles, only those who could adapt to extreme conditions survived. Saurischia dominated the hunting niches. In the late Triassic fossil record, species such as Coelophysis appear, a light predator that hunted in groups and already displayed the elegance of the design that would characterize Jurassic theropods. It had a slender body, flexible neck, and strong hind limbs that allowed it to strike prey with surgical precision. Its skeleton reveals a relatively large brain, indicating advanced coordination and vision. It was the embodiment of the modern hunter in a still ancient world. Sauropodomorphs, on the other hand, relied on mass and longevity. Their strategy was simple: grow until untouchable. Plateosaurus, up to 9 meters long, stood on its hind legs to reach the tops of conifers. Its neck and tail acted as perfect counterweights, a natural architecture that foreshadowed the magnificence of Jurassic giants. In them, evolution experimented with size as a defense mechanism. And it worked. No terrestrial predator of the Triassic could bring down a healthy adult. Meanwhile, ornithischians slowly expanded into ecological margins, riverbanks, plains, and arid zones. They were smaller animals, but their innovation lay in the mouth. Lesothosaurus, one of the first of its lineage, possessed a set of teeth specialized for cutting leaves and fibrous stems, a design that anticipated the complex dentition of Cretaceous herbivores. Its wide pelvis and capacity to store large volumes of food made it an efficient biological processor, a slow-digesting factory that transformed Triassic plants into pure energy. Over time, the differences between the two groups became insurmountable. Saurischians developed a more active physiology, probably warm-blooded, which allowed them constant mobility. Ornithischians, meanwhile, perfected their bony armor and their ability to form herds, finding strength in numbers. It was the biological balance of two opposing philosophies: movement and defense, hunting and endurance, solitude and cooperation. Modern paleontology has revealed that this division was not only anatomical but also respiratory. Saurischians had an air sac system connected to their lungs, similar to birds, allowing continuous oxygen flow. This would explain how they could maintain high activity even in low oxygen conditions. Ornithischians, for their part, developed reinforced internal cavities to better support weight and protect vital organs. Every structure, every bone, responded to a specific environmental need. This separation would shape the entire Mesozoic era. Saurischians dominated the tropics and coastal areas where prey was abundant. Ornithischians, more patient, thrived in inland regions where plants were tough and water scarce. With the progressive fragmentation of Pangaea, both groups began to diverge geographically. New ecosystems emerged, and with them, new forms of life. The future lands of America, Africa, Asia, and Europe were populated by unique species that followed the same evolutionary rules, but in different settings. Paleontologists still debate the exact origins of this division, as some recent studies suggest that the classic model may not be so clear, and that certain primitive ornithischians share more affinities with theropods than previously thought. However, beyond modern reinterpretations, the mark of that separation remains visible in every fossil: two opposing anatomical designs, two survival strategies that coexisted for millions of years without driving each other to extinction. In the twilight of the late Triassic, ecosystems were in precarious balance, and any small change could break this fragility. The Middle Triassic and the struggle for survival. The Triassic was an era of reconstruction. The planet, still scarred by the Great Permian extinction, was slowly recovering. Life had returned to colonize deserts, swamps, and inland seas, but every new ecosystem was a battlefield. Each emerging species had to compete with remnants of former dominance and with new life forms striving to occupy empty niches. Survival was not a right, it was a constant challenge. Dinosaurs, still scarce and small, were not the masters of the world. They shared the valleys, plains, and primitive forests with formidable creatures. Rauisuchians, distant relatives of modern crocodiles, walked upright on their hind legs and could reach 6 meters in length. Etosaurs, covered in bony plates, foraged on the ground for roots. And synapsids, the so-called mammal-like reptiles, still survived in burrows or in the shadows of swamps. It was a time when the Earth seemed undecided between past and future. In this scenario, dinosaurs struggled to carve out a space. Their advantage was efficiency. Legs positioned under the body allowed them to move quickly and cover long distances without exhaustion. Their skeleton, lighter and pneumatic, enabled more consistent respiration. And although they were neither the largest nor the strongest, their endurance gave them an edge on a planet alternating between fire and drought. The Middle Triassic, between 247 and 237 million years ago, was an era of climatic transition. The planet was warming under a dense carbon dioxide atmosphere. Summers were scorching, winters dry and cold. Tropical jungles had shrunk, leaving vast deserts of red earth. Herbivores moved between ephemeral oases. and carnivores lurked in the shadows. It was a silent but constant struggle. Each dawn brought the possibility of extinction. In the swamps and rivers of what is now southern Africa, some of the first primitive plateosaurians emerged, herbivorous dinosaurs beginning to dominate the landscape. They were bipedal, long-necked, and could feed on both low vegetation and high branches. The ability to rise on their hind legs to reach leaves was an evolutionary innovation that distinguished them from earlier reptilian herbivores. Each of their movements represented a step toward the Jurassic future, but they were not alone. On the plains of Pangaea, Rauisuchians like Postosuchus reigned as supreme predators. Their bodies were designed for hunting, powerful muscles, rigid tails, and devastating bites. They ambushed prey, hiding in dry vegetation to strike with precision. Fossils found in North America and Europe show a creature that seemed to anticipate the ferocity of future large carnivores, but with a more archaic design. They were the temporary masters of the food chain, and young dinosaurs had to avoid crossing paths with them. In the humid coasts and inland lakes, life flourished timidly. Temnospondyle amphibians, some over 3 meters long, lurked in the water. They were distant heirs of the first terrestrial vertebrates, survivors of a lineage that had dominated swamps for millions of years. But their time was running out. Increasingly arid climate changes reduced aquatic habitats. Evolution was shifting toward fully terrestrial animals, and at that point, dinosaurs had all the advantages. The skies, in turn, began to fill with new creatures. Pterosaurs, the first flying vertebrates, appeared toward the end of the Middle Triassic. Their wings, formed by a membrane supported by an enormously elongated finger, allowed them to glide over rivers and coasts in search of fish or insects. They were fragile, but their mastery of the air gave them a perspective no other creature possessed. At that time, dinosaurs had not yet conquered the skies, but the concept of flight already existed, suspended above them, foreshadowing a future that only some would reach. Life in the Triassic was a precarious balance. At night, temperatures dropped drastically, and the heat of the day was not enough to sustain large populations. When rains came, they arrived violently, scouring the ground and nests. In that environment, adaptability was the most valuable currency. Dinosaurs, with their more active metabolism, withstood extreme fluctuations better than their competitors. Unlike synapsids, which relied on burrows and shelters, they could survive in the open, migrating according to the season or the hunt. Ecosystems were organized into short, brutal cycles. Herbivores fed carnivores, and carnivores in turn nourished the decomposers that enriched the soil. Everything depended on the delicate pulse of the rains. When these failed, the desert expanded and bodies were left exposed to the sun, becoming future fossils. Under these extreme conditions, dinosaurs demonstrated a capacity for endurance that would be key to their later expansion. They not only survived, but multiplied. Toward the end of the Middle Triassic, the first complex communities began to form. Small groups of coelophysis, slender and fast carnivorous dinosaurs, hunted in packs. Fossil evidence found in New Mexico shows concentrations of skeletons suggesting gregarious behavior. This early cooperation changed the rules of the game. For the first time, social intelligence began to weigh as much as physical strength. Predators were no longer solitary. They learned to plan. In the most fertile areas of Pangaea, conifer and cycad forests stretched among dunes and ephemeral lagoons. There, herbivorous dinosaurs found refuge and food. In these spaces, the balance between species reached a point of stability. Herbivores cleaned the forests, carnivores controlled their populations, and decomposers maintained soil fertility. Earth seemed to have found a new biological harmony, but this calm was only the prelude to a storm. Deep within the planet, volcanoes were building pressure. Along the edges of Pangaea, magma slowly forced its way upward. Massive eruptions in the regions of present-day Brazil and Africa would soon release tons of gases into the atmosphere, unleashing a climatic imbalance that would trigger one of the most decisive extinctions in the history of life. But dinosaurs, already adapted to the extreme fluctuations of the Middle Triassic, would be the only ones prepared to endure. The Triassic-Jurassic extinction. 201 million years ago, the planet entered an era of fire. What began as a series of localized eruptions ended up becoming one of the most colossal volcanic events in Earth's geological history. The tectonic plates holding the supercontinent Pangaea together began to fracture, opening incandescent cracks thousands of kilometers long. From these wounds flowed an ocean of magma, a slow but unstoppable current that released clouds of carbon dioxide, sulfur, and ash into the sky. The atmosphere became unbreathable, the seas acidified, and the Triassic skies took on a permanent reddish hue. Ecosystems, already fragile after millions of years of droughts and thermal oscillations, collapsed one after another. What followed was a mass extinction, the fourth major biological catastrophe in the planet's history. More than 70% of terrestrial and marine species disappeared in less than 1 million years. The oceans lost their ammonites and primitive corals, the continents, their giant amphibians and dominant reptiles. The balance that had kept the world standing since the end of the Permian collapsed. The exact causes are still debated, but evidence points to a primary culprit: massive volcanism in the Central Atlantic. The colossal eruptions formed what is now known as the Central Atlantic Magmatic Province, or CAMP, a vast basaltic formation covering regions of South America, Africa, and North America. Each of these eruptions could have released more carbon dioxide than all of modern humanity produces in hundreds of thousands of years. The result was a sudden rise in global temperatures and a chemical collapse in the oceans. Carbon isotope records in marine sediments show an abrupt shift, an unmistakable signal of a planet suffocating under greenhouse gases. Temperatures rose between 4 and 8 degrees, the poles melted, and sea levels increased drastically. Rains became acidic, destroying forests and altering the pH of rivers. The food chain broke from the bottom up. Plants could not withstand the climatic fluctuations. Herbivores starved and carnivores were left without prey. On land, Rauisuchians, the ancient predators of the Triassic, almost completely disappeared. Large amphibians, dependent on wet environments, also vanished. The most primitive marine reptiles, unable to withstand changes in salinity and acidity, went extinct without leaving descendants. Only a few groups, such as small crocodilians and the first insectivorous mammals, survived, hiding in burrows or areas less affected by volcanic gases. But there was one group that not only endured but took advantage of the chaos: dinosaurs. Their triumph was not immediate, but it was decisive. Thanks to their more efficient, probably endothermic physiology and their ability to travel long distances in search of food, they survived the cataclysm with an evolutionary advantage over the rest. As the planet suffocated, smaller dinosaurs found refuge in the newly fragmented landscapes. Their active metabolism, upright posture, and advanced respiratory system allowed them to withstand low oxygen and high temperatures. Where others fell, they kept moving. The seas, by contrast, became graveyards. Excess dissolved carbon dioxide in the water caused extreme acidification, destroying shells, reefs, and calcareous plankton. With the marine ecosystem's base collapsed, entire food chains crumbled. The extinction was so rapid that in some strata, paleontologists have found sediment layers without any fossil traces, biological deserts compressed into stone. For tens of thousands of years, the planet was a wasteland. On the continents, acidic rains swept through the forests, leaving only scattered conifers and hardy ferns. Fires, triggered by lightning storms and flammable gases released from the subsoil, blanketed the sky with soot. The sun barely penetrated the dense smoke layer, and after a scorching peak, temperatures dropped abruptly. It was a volcanic winter. In this devastated scenario, the creatures that survived adapted to a shadowed world. In present-day Greenland, fossil records from that time reveal something extraordinary: the footprints of small dinosaurs crossing a landscape covered in ash. These were traces of hope on a desolate planet. These footprints belonged to the first early Jurassic theropods and sauropods. They had endured the inferno and were now spreading across an almost empty world. Their competition had vanished. Ecological niches were vacant. For the first time, dinosaurs became the true masters of Earth. The Triassic-Jurassic extinction was not just an end, but an evolutionary purge. It eliminated creatures dependent on stable conditions and cleared the way for those that could withstand constant change. Dinosaurs, forged in adversity, proved to be the most resilient life form of their time. In just a few million years, their diversity multiplied. Herbivores grew in size, carnivores refined their hunting strategies, and new species occupied every corner of the planet. The devastated Earth transformed into a laboratory of gigantism and adaptation. Geological records reveal that after the cataclysm, carbon dioxide levels began to gradually decrease. Plants recovered, forests expanded once more, and ecosystems were reborn under new rules. It was the dawn of the Jurassic, an era of climatic stability and plant abundance. Rains returned strongly, rivers multiplied, and seas teemed with life. In this new scenario, dinosaurs found the ideal conditions to thrive. The landscape of Earth changed radically. Where deserts had once dominated, temperate forests emerged. Conifers, ginkgos, and cycads formed vast green expanses, feeding the first giant herbivores. The continents, still close together, allowed species to migrate freely, colonizing distant territories. In just a few million years, dinosaurs diversified beyond all comparison. Sauropods dominated the plains, theropods hunted in packs, and ornithischians began evolving new defenses. Jurassic dominance. When the Triassic smoke cleared, the world awoke different. Earth had transformed into a green, warm, and lush planet. Rainfall was frequent, seas spread over the newly fractured continents, and volcanoes, exhausted after millennia of activity, were silent. The atmosphere, now more stable, contained rising oxygen levels. It was the start of the Jurassic, an era of biological rebirth where dinosaurs, having survived the chaos, became the true rulers of the planet. On the plains, herbivores grew to colossal dimensions. The first sauropods, descendants of the ancient Plateosaurus, developed necks capable of reaching the tops of the tallest trees. Diplodocus, over 25 meters long, moved like a living tower among the conifer forests. Its neck was a structure of evolutionary precision, hollow vertebrae to reduce weight, elastic tendons acting as counterweights, and an efficient respiratory system similar to modern birds, maintaining a constant airflow. Feeding no longer required competing on the ground. The sky itself had become their table. Beside it, Brachiosaurus defied the proportions of animal bodies. With an upright neck and forelimbs longer than its hind limbs, it could reach heights over 13 meters. It was the titan of its time, a peaceful giant requiring tons of leaves each day to survive. Its heart, the size of a modern car, had to pump blood at enormous pressure to keep its brain supplied. The anatomy of these colossi was not just a curiosity, it was a statement of supremacy. In a world without predators capable of taking them down, size was their best defense. Carnivores, however, were not far behind. Theropods, heirs of the ancient Coelophysis, evolved into larger, faster, and deadlier forms. Allosaurus, the emblematic predator of the Jurassic, dominated the northern hemisphere plains. It measured over 8 meters long and had jaws capable of tearing flesh with devastating force. It hunted alone or in small groups, stalking from the shadows of the forests. Its forward-facing eyes provided stereoscopic vision, an advanced trait that allowed it to calculate distances with deadly precision. The Jurassic was not only the age of giants, but also of abundance. Forests stretched across fragmented Pangaea. America, Africa, and Eurasia were now territories separated by young seas. This geographic isolation promoted an evolutionary explosion. In each region, new dinosaur species emerged, adapted to their particular environments. Humid climates and predictable seasons allowed populations to grow uninterrupted. The planet was a fertile garden, and dinosaurs its gardeners and predators. Ornithischians, for their part, began to flourish in this era. Stegosaurus, with its iconic dorsal plates and spiked tail, roamed the plains of western North America. Despite its intimidating appearance, it was a slow and selective herbivore, feeding on ferns and cycads. The plates on its back, irrigated by blood vessels, may have functioned as thermal radiators or display structures. Every movement of its body was a lesson in biological engineering, an adaptation that balanced defense, thermoregulation, and visual communication. The seas also experienced their own heyday. There, ichthyosaurs reigned, marine reptiles with hydrodynamic bodies reminiscent of modern dolphins. Some reached 20 meters in length, hunting fish and cephalopods in the warm waters of the Middle Jurassic. Alongside them swam plesiosaurs with their long serpentine necks and pliosaurs, with jaws capable of crushing sharks. The planet's waters mirrored its surface, a kingdom of colossi and predators. In the skies, pterosaurs expanded gracefully. Species such as Rhamphorhynchus and Pterodactylus glided through the air with membranous wings supported by an elongated fourth finger. Some were coastal fishers, others were opportunistic scavengers following terrestrial predators. Their presence marked the beginning of aerial competition that, millions of years later, would lead to an astonishing innovation: the true flight of birds. But the true secret of Jurassic success did not lie solely in size or strength, but in the diversity of strategies. Dinosaurs had learned to occupy every corner of the planet. In the tropics, small, agile theropods hunted insects and lizards. In temperate regions, enormous sauropods cleared entire forests. Some groups, such as the Compsognathids, did not exceed 70 centimeters and moved among the remains of large predators' prey, playing an essential ecological role. On the shores of lakes, the first dinosaurs with rudimentary feathers hunted under the rain, their bodies covered with fine hair that retained heat. The natural balance of the Jurassic was a symphony of ecological interaction. Herds of herbivores, as they moved, created clearings that favored the growth of new plants. Carnivores controlled their populations. Carcasses fed insects, scavengers, and decomposers, which in turn returned nutrients to the soil. It was a closed, self-sufficient system that functioned with precision for millions of years. Life had reached a point of stability unknown to the planet since before the Permian. However, absolute dominance is never eternal. Beneath the surface, tectonic forces continued their silent work. The continents drifted further apart, opening a new ocean, the Atlantic. This geological movement would alter ocean currents, regional climates, and species distribution. Some populations became isolated, giving rise to new forms. Others disappeared slowly, unable to adapt to the changes. The balance was beginning to tilt again. In the final millions of years of the Jurassic, the air became more humid and the forests denser. Sauropods concentrated in open regions, while carnivores adapted to hunt in the thickets. In China, small feathered theropods appeared, such as Anchiornis, a prelude to a biological revolution that would change the course of evolutionary history. Among them, some experimented with jumping, gliding, and air control. Wings were about to be born. Diversity of behaviors and societies. In the vast world of the Jurassic, dinosaurs were no longer mere solitary beasts driven by instinct. Fossil evidence reveals that many had reached a level of complex behavior, with social structures, hierarchies, cooperation, and even parental care. On a planet where size guaranteed survival, collective intelligence became another great evolutionary tool. Life had learned that sometimes survival did not depend on strength, but on unity. Fossilized footprints found in the Winton Desert in Australia show parallel tracks of sauropods moving in the same direction. These marks were not random. They formed organized paths, with adults in the center and juveniles protected at the sides. This arrangement suggests herd movement. In regions where predators lurked, giant herbivores traveled together, forming living walls. It was an instinctive but effective strategy. Each step demonstrated the coordination of a species that, despite its size, understood the strength of the group. The same pattern repeats on other continents. In Wyoming, tracks of Diplodocus and Apatosaurus appear grouped, always near ancient water sources. The behavior indicates seasonal migrations, massive movements in search of fresh vegetation. On these journeys, adults probably guided the group while the young learned the routes they would follow for life. The biology of care and the transmission of experience began to shape intergenerational relationships. In the fossil record of Asia, small carnivores such as Coelurus and Compsognathus also show signs of social behavior. Their remains appear together, possibly evidence of group hunting or communities sharing territory. Cooperation among medium-sized predators would have been an advantage against increasingly large and organized prey. In a world of giants, the small discovered that intelligence was their best weapon. The most direct evidence of parental care comes from the Maiasaura fossil, discovered millions of years later in the Cretaceous, but it allows us to infer behavior that originated in the Jurassic. Nests with eggs, newly hatched young, and the remains of adults nearby reveal something new: family protection. The instinct to nest to safeguard offspring already existed in earlier lineages, such as the early Jurassic prosauropods. Some fossils show eggs grouped in circular structures, carefully covered with soil or vegetation. In them, life had learned to plan for the future. Communication among dinosaurs, though impossible to observe directly, can be inferred from the shapes of their bodies. Crests, horns, and dorsal plates were not merely ornamental. In species such as Stegosaurus or Dilophosaurus, their symmetrical arrangement and vascularization suggest use in visual or thermal signaling. Crests could change color when heated by the sun or filled with blood, serving to intimidate, attract mates, or establish dominance. In the dim light of Jurassic forests, a display of color or a roar could decide the outcome of a confrontation without violence. Sounds were also part of this language. Some dinosaurs had elongated or hollow nasal structures like Camarasaurus, capable of resonating with air. These cavities functioned as acoustic chambers, producing deep sounds that could travel long distances. On mist-covered plains, these roars were signals of identity, warnings, or mating calls. The echoes of those lost voices still resonate in stone. Social organization also implied hierarchies. In groups of carnivores like Allosaurus, cooperation during hunting could coexist with internal competition. Bite marks between individuals of similar size, found in fossils, suggest fights for leadership or access to carrion. Nature did not abandon violence but learned to channel it. Dominance was imposed not only by force but through intimidation and ritual. This was the prelude to more sophisticated social behaviors that millions of years later would reach full expression in birds. Gregarious behavior also transformed ecosystems. In the fertile regions of North America and Africa, herds of herbivores moved along seasonal routes, creating clearings in forests that favored plant regeneration. Migration became an ecological engine. The constant movement of thousands of bodies altered landscapes, redistributed nutrients, and shaped the habitats of other species. Sauropod footprints created depressions that after rains became ponds. Each journey left a mark that changed the environment forever. Coexistence between species was not always peaceful. In some late Jurassic sites, the remains of herbivores and carnivores appear mixed, evidence of failed hunts or accidental encounters around water sources. In the Jurassic world, the line between predator and prey was constantly crossed. Yet even in these clashes, collective intelligence prevailed. Herbivores formed defensive circles. Predators attacked in coordinated directions. Evolution had become a strategic board. Not all social behaviors were altruistic. Some small carnivores developed kleptoparasitism, stealing prey caught by others. In environments where resources were abundant but competitive, this strategy ensured food without risk. Other species specialized in scavenging, following large predators at a distance. It was an invisible network of interaction. The hunter, the opportunist, and the cleaner shared the same stage. The idea of the dinosaur as a crude, solitary being was left behind. Anatomical evidence and fossil traces show that many species had proportionally large brains, developed olfactory lobes, and keen eyesight. The Jurassic was an era of behavioral evolution, not just of the body. The first signs of cooperation, communication, and parental care were the foundations of modern animal societies. Within them, a primitive collective intelligence was taking shape, shared learning across generations. At the edges of the Jurassic, while herds roamed the plains and hunters stalked beneath ferns, something entirely new began to emerge in the branches of the smallest lineages. Some theropods developed filamentous structures on their skin, an innovation that would forever change the course of biology. The evolution of feathers and the origin of birds. The story of flight did not begin in the sky, but on the ground. Among late Jurassic theropods, small, agile hunters with precise movements began developing a new type of body covering. It was neither skin, scales, nor hair. They were fine keratin filaments, soft and light, extending from the back, arms, and tail. They were the first feathers. Their initial purpose was not flight, but insulation, temperature regulation, and possibly communication. Yet these structures, born of necessity, would become the greatest evolutionary leap since life left the sea. In the humid forests of what is now China, around 160 million years ago, these small dinosaurs scurried among ferns and conifers. One of them, Anchiornis huxleyi, measured just 40 centimeters and was covered with short body feathers, though longer ones adorned its arms and legs. It could not fly, but used its feathered limbs to glide short distances or control descent from a branch. It was an evolutionary experiment, an intermediate form between leaping and flying. The next step was taken by an animal that would become one of the most famous fossils in history, Archaeopteryx lithographica. Discovered in 1861 in the limestone quarries of Solnhofen, Germany, this fossil united two worlds for the first time, dinosaurs and birds. It measured 1/2 meter long, had teeth in its jaws, claws on its wings, and a long bony tail, but its body was covered with asymmetrical feathers designed to generate lift. Archaeopteryx could not only glide, it could flap its wings. It was the first known flight in the history of the planet. Feathers, like scales, originated from keratinous epidermal structures, but evolution refined them into perfect aerodynamic mechanisms. In their most primitive form, they were simple filaments. Later, they branched into more complex structures with a central shaft, barbs, and barbules that interlocked like a natural zipper. Each feather was a biological engineering system designed to combine lightness and strength. Unlike pterosaur membranes, feathers could be repaired, replaced, and adapted to the environment. Flight did not arise from a single impulse. There are two main theories about how feathered dinosaurs developed it: the trees-down hypothesis and the ground-up hypothesis. The first proposes that small arboreal theropods like Microraptor used their feathers to glide from tree to tree, perfecting air control until achieving active flight. The second suggests that terrestrial runners, when leaping to catch prey or escape predators, began flapping their feathered arms to gain lift. Both paths, different yet complementary, could converge on the same result: an animal capable of mastering the air. Microraptor guy, found in China and dated to 120 million years ago, represents one of the most beautiful and revealing forms of this process. It had long feathers not only on its arms but also on its legs, forming a strange four-wing design. Its asymmetrical feathers and small sternum indicate it could glide long distances with precision, controlling the air with subtle movements. Its body was light and its feathered tail acted as a rudder. In it, flight ceased to be an accident and became an art. The development of feathers also transformed physiology. Feathered theropods required high energy levels to maintain body temperature. This implied a faster metabolism, more efficient lungs, and a stronger heart. Bone evidence suggests that many of these animals were warm-blooded, capable of maintaining a constant temperature even in cold environments. This combination of active metabolism, hollow bones, and insulating feathers marked the birth of a different lineage: birds. But flight came at a price. Aerodynamic adaptations demanded lightness. Bones became thin and pneumatized, with internal cavities connected to the respiratory system. The sternum expanded to anchor powerful pectoral muscles, and the tail reduced into a compact structure. The pygostyle, jaws with teeth, disappeared, replaced by keratinous beaks. In just a few million years, nature had completely redesigned the bodies of the ancient theropods. Confucius ornis, one of the earliest true birds of the early Cretaceous, already displayed a skeleton fully adapted for flight. It lacked teeth and had a sharp beak. Its skeleton was light and its wings folded precisely over the body. Flight was no longer an occasional leap but a daily habit, and with it came intelligence. The balance required for flying, the coordination of the wings, the spatial memory to return to the nest, all this drove brain development. In this transitional process, some species remained at the margins. Dromaeosaurs, like Velociraptor, shared a common ancestor with birds but retained a terrestrial lifestyle. Their aerodynamic bodies and feathers were not for flight but for temperature regulation and communication. Feathers also became a visual language. Males displayed colors and shapes to attract mates or mark territory. Flight was not the only possible outcome. Feathers had acquired multiple biological and social functions. The impact of this transformation went beyond anatomy. For the first time, a group of animals conquered the third element, air. The Earth, until then dominated by walkers and swimmers, became populated by beings capable of moving between trees and clouds. The skies of the early Cretaceous were filled with primitive birds gliding alongside pterosaurs, sharing a space that had previously belonged only to them. But while pterosaurs relied on the wind, birds learned to control it. Flight also changed survival strategies. Primitive birds could escape large terrestrial predators, forage in inaccessible areas, and colonize remote islands. Natural selection favored intelligence, keen vision, and memory. Birds learned routes, migrations, and seasonal patterns. In them, evolution had found the ultimate expression of mobility. The fossil record shows that birds did not merely descend from dinosaurs, they were dinosaurs. Feathered theropods with their light skeletons, unidirectional flow lungs, and high metabolism share all the essential traits with modern birds. They were not a rupture but a continuity. Flight was simply the latest innovation of a lineage that had learned again and again to adapt better than anyone else. The Mesozoic sky filled with swift and colorful silhouettes. Some hunted insects among the trees, others fed on fish in lakes. While giant herbivores continued their reign on land, a new empire rose in the air. Dinosaurs had conquered the ground, the sea, and finally, the sky. But beneath this apparent harmony, the planet continued to change. New floras emerged, continents shifted, and biodiversity reached its peak. The Cretaceous, the golden age of diversity. The Cretaceous was the culmination of the age of dinosaurs, a time of splendor when life reached its maximum diversity and complexity before the decline. The planet, warm and humid, was fragmented into defined continents. North and South America were slowly separating. Africa was moving away from South America. Europe, Asia, and Antarctica formed mosaics of islands and inland seas. Ocean currents were gentle, the poles lacked ice, and vegetation flourished luxuriantly. It was a world of vivid colors and beings approaching evolutionary perfection. During the first millions of years of the Cretaceous, flowering plants, called angiosperms, began to spread. This silent revolution transformed the landscape and the food chain. Forests were filled with scents, nectar, and fruits, attracting insects, birds, and small mammals. Around them, a new ecological network formed, benefiting herbivores and consequently their predators. Nature had invented beauty as a survival strategy. Among herbivores, hadrosaurs, or duck-billed dinosaurs, became one of the most successful species. They had batteries of hundreds of replaceable teeth capable of grinding tough vegetation with astonishing efficiency. They lived in large herds and migrated following seasonal cycles. Some, like Corythosaurus, had hollow cranial crests that functioned as natural trumpets. Their calls resonated through valleys as social signals or mating rituals. In the golden age of dinosaurs, sound was part of the language of life. Ceratopsids, such as the imposing Triceratops, dominated the plains at the end of the Cretaceous. Their 3 horns and massive bony frill were not only defensive weapons, but also symbols of hierarchy and display. Fossils of multiple individuals together suggest group structures and cooperative defense. With a mass of up to 10 tons, these giant herbivores could face the era's most feared predators and withstand direct attacks thanks to their reinforced necks and fused vertebrae. They were as imposing as they were disciplined. In the skies, primitive birds had already achieved remarkable diversity. Some, like Ichthyornis, hunted fish with toothed beaks. Others, like Hesperornis, had lost the ability to fly and became expert swimmers. Air and sea were linked by the same lineage. Birds were no longer an evolutionary curiosity. They were a dominant presence, as well adapted to the environment as the large reptiles still ruling the earth. The throne of predators was occupied by theropods, and among them stood the undisputed king, Tyrannosaurus rex. Over 12 meters long, with a bite capable of exerting more than 6 tons of pressure, it was the ultimate result of millions of years of carnivorous refinement. Its massive yet lightweight skull housed acute senses, excellent vision, an extraordinary sense of smell and sensory coordination that made it a perfect hunting machine. Yet it did not always hunt. Fossil evidence shows it also scavenged, taking advantage of any opportunity in an ecosystem where even kings had to adapt to survive. But not everything was brutality. In the forests of the northern hemisphere, dromaeosaurs like Velociraptor and Deinonychus displayed intelligence and precision. Their sickle-shaped claws could easily tear flesh, but their success lay in strategy. They hunted in groups, coordinating attacks with surgical speed. Agile, fast, and probably covered in feathers, they were the closest heirs of the small hunters that had conquered the air, sharing the same basic anatomical structure as birds. If Tyrannosaurus rex was force, they were mind. In the oceans, competition was no less fierce. Mosasaurs, marine reptiles that appeared in the mid-Cretaceous, replaced the ancient ichthyosaurs and pliosaurs. Their serpentine bodies and articulated jaws allowed them to swallow prey whole. Some reached 18 meters in length, hunting sharks, fish, and even other mosasaurs. The sea was a silent battlefield where each species represented a different survival strategy. The depths of the Cretaceous were as dominated by predators as the terrestrial surface. Flora also changed the global balance. Flowering plants not only provided food, but altered the composition of the air, increasing oxygen and reducing carbon dioxide. Climates stabilized and ecosystems diversified further. Mixed forests of conifers, palms, and angiosperms created habitats for countless small species, insects, birds, early mammals, and reptiles. The base of life expanded and the ecological pyramid rose toward increasingly specialized forms. As the Cretaceous progressed, continents continued their slow drift. The separation of North America and Eurasia isolated entire dinosaur populations which evolved along different paths. In Asia, Tarbosaurus bata, a close relative of T. rex, ruled the steppes. In South America, abelisaurids with tiny arms and ornamented skulls became the supreme hunters. Every corner of the planet had its own lineage of giants adapted to the local climate and flora. But the Cretaceous was not only an age of grandeur, it was also a time of fierce competition and extreme specialization. Food chains became fragile, dependent on precise climatic and plant cycles. Any disruption such as a drought, a temperature change, or a volcanic eruption could destabilize entire ecosystems. Geological records from the end of the Cretaceous already show signs of environmental stress, fluctuations in sea levels, increasing volcanic activity, and a gradual decline in marine diversity. The Earth was unknowingly preparing the stage for its next tragedy, yet for tens of millions of years life continued to flourish. In the late Cretaceous, landscapes were of a beauty and complexity the planet would never know again. Herds of hadrosaurs waded through shallow rivers followed by stealthy carnivores. Birds flew among palms and ferns. Mosasaurs emerged from the waves in search of prey. The sky, land, and sea were a single theater of continuous motion. The biosphere had reached its most dynamic balance. The world of the dinosaurs was at its peak. They were larger, more diverse, and more numerous than ever. Their behaviors were sophisticated and their interactions complex. Coexistence with other animals. During the golden age of the Cretaceous, dinosaurs were not alone. In every corner of the planet, they shared dominion with a multitude of creatures that, although often overshadowed by giants, were essential to the natural balance. In the skies, pterosaurs still reigned as masters of flight. In the seas, plesiosaurs and mosasaurs ruled the depths. And beneath the earth, small nocturnal mammals wove the future in silence. It was a planet teeming with life, where every element of the ecosystem depended on interaction with others. Pterosaurs, the first vertebrates to conquer the air, continued dominating the skies, though now they shared space with primitive birds. Since the Triassic, they had evolved into astonishing diversity. By the mid-Cretaceous, some species reached colossal sizes. Quetzalcoatlus northropi, found in North America, could exceed 10 meters in wingspan. With a neck as long as a giraffe's and a head as sharp as a spear, it fed on fish and small vertebrates, gliding for hours over the warm plains of the Western Hemisphere. Its flight combined elegance and power, propelled by membranous wings supported by a single enormous finger. In coastal skies, Pteranodon, with its elongated bony crests, soared over sea winds in search of fish. Its lifestyle resembles that of modern albatrosses, air nomads that rarely touched land. Despite their intimidating appearance, many pterosaurs were graceful and specialized creatures, with light musculature and fast metabolism. Some even developed fine down called pycnofibers, a type of fluff that helped conserve body heat, a reminder that nature continued experimenting with the same biological solutions that had given rise to bird flight. Meanwhile, the Cretaceous seas were a realm of their own. Oceans covered large parts of the continents and were populated by marine reptiles of titanic proportions. Plesiosaurs, with long necks and wide bodies, swam slowly among schools of fish, propelled by turtle-like flippers. Some, like Elasmosaurus, reached up to 15 meters. Their movements were slow, but their size deterred almost all predators. In contrast, pliosaurs, their close relatives, were fierce predators with short necks and massive heads, capable of crushing sharks whole. Kronosaurus, one of the largest, reigned over Australian seas as an unstoppable force, devouring everything in its path. Later in the Cretaceous, a new family emerged to replace them. Mosasaurs. Descended from terrestrial lizards adapted to aquatic life, they became the most formidable marine predators of their time. With elongated bodies, articulated jaws, and a fin-shaped tail, they were agile hunters that could reach astonishing underwater speeds. Mosasaurus hoffmanni, the namesake of the group, exceeded 17 meters in length and had double-rowed teeth capable of holding and tearing prey with no chance of escape. In the depths, the roar of T-Rex had no echo, but its underwater equivalent was the Mosasaurus. Above ground, the Cretaceous tropical forests buzzed with insect life. Giant dragonflies, primitive bees, and pollinating beetles thrived alongside the new flowering plants. The exchange between flora and insects created an unprecedented ecological bond, pollination. This symbiotic relationship transformed the planet, accelerating plant expansion and feeding a new generation of herbivores. On tree trunks, ants began organizing colonies, and termites built earthen structures that withstood the test of time. Every creature, no matter how small, played a role in the grand machinery of Mesozoic life. Among roots and burrows, primitive mammals quietly endured the supremacy of the dinosaurs. Small, nocturnal, with keen senses and proportionally large brains, they fed on insects, eggs, and tiny reptiles. Some, like Repenomamus, reached the size of a badger and were bold enough to prey on dinosaur hatchlings. Though marginal in number, their adaptability was extraordinary. Their endothermic physiology, fur, and ability to give birth to live young ensured their survival beyond the end of the Mesozoic. In swamps and rivers, crocodilomorphs remained witnesses to all eras. Surviving every cataclysm since the Triassic, they reached new forms in the Cretaceous. Some, like Sarcosuchus imperator, exceeded 12 meters and could confront even medium-sized dinosaurs along African lake shores. Their thick skin, ton force bite, and infinite patience made them perfect predators. Unlike dinosaurs, their evolutionary strategy was not change, but permanence. Their design was so effective that it would need almost no alteration for the next 100 million years. The coexistence of these worlds, air, land, and sea, was a delicate ecological balance. Pterosaurs depended on the fish hunted by mosasaurs, insects pollinated the flowers that fed herbivores, and mammals fed on eggs left behind by dinosaurs. It was an interdependent web, a biological symphony that kept the pulse of the planet alive. Life had reached its maximum complexity before the end, yet even in that apparent harmony, change never ceased. Continental plates continued their drift, opening new inland seas. Volcanoes spewed gases into the atmosphere, altering the climate. In the polar regions, heat began to recede. The planet was slowly cooling, forests shifted toward the equator, and animal migrations intensified. Fossil records from the end of the Cretaceous reveal a disturbing pattern, a decline in marine diversity, and the gradual disappearance of plankton species, the base of the food chain. Something distant and silent was disturbing the balance. The dinosaurs, oblivious to the looming danger, continued their reign with the indifference of those who believed themselves eternal. Yet the ground beneath their feet was changing. A world changing underfoot. The Cretaceous was advancing toward its end, and the Earth was transforming once again. The continents were no longer scattered fragments of Pangaea, but independent land masses slowly moving over a fiery sea of magma. North America was drifting away from Europe, South America was separating from Africa, India had begun its solitary journey northward. The planet's geography was shifting beneath the dinosaurs' feet, and with it, everything they knew. What had been a world of interconnected forests and plains was turning into an archipelago of isolated ecosystems, each with its own survival rules. Inland seas covered large portions of North America. The Niobrara Sea, a tropical ocean that split the continent in two, stretched from the Gulf of Mexico to the Arctic. Its waters were home to mosasaurs, hesperornis, and primitive sharks, while along the shores, herds of hadrosaurs drank beside crocodilomorphs. It was a vibrant but unstable world. Tides rose and fell with unusual frequency, climates varied violently, and ecosystems reorganized every few thousand years. The stability of the Jurassic was a thing of the past. In the air, giant pterosaurs dominated the wind, but their diversity was beginning to wane. Birds, smaller and more versatile, adapted better to sudden temperature changes. Some migrated with the seasons, others nested on cliffs and coasts. In the competition for the skies, lightness was favored over wingspan. It was a sign that the Mesozoic balance was starting to crack. On land, large herbivores still ruled the continents. Triceratops and ankylosaurs moved in groups, hadrosaurs migrated following rainfall and flowering cycles, and titanosaurs in South America dominated the open plains. But their size, once an advantage, was slowly becoming a liability. Climatic changes shortened periods of abundance, forests retreated, and deserts expanded. Feeding a body weighing tens of tons became increasingly difficult. Predators, in contrast, seemed to thrive. Tyrannosaurus rex in the north, along with its counterparts in Asia and South America, became the supreme hunters of a planet already showing signs of decay. Their reign coincided with the last splendors of Mesozoic life, vast ecosystems still roaring with power even as their foundations were on the verge of collapse. Volcanoes played a silent but decisive role. In what is now India, a massive volcanic system, the Deccan Traps, began releasing toxic gases and enormous amounts of carbon dioxide. For over 1 million years, lava flows covered thousands of square kilometers, sending ash clouds into the atmosphere that partially blocked sunlight. Global temperatures fluctuated violently, first rising, then dropping abruptly. The most sensitive plants disappeared along with the insects that pollinated them. Food chains began to fracture slowly, starting at the base. Fossils from the end of the Cretaceous reveal a worrying trend, a progressive reduction in species variety. It was not a sudden disappearance, but an accumulated wear. Some dinosaur species reproduced more slowly, others migrated to more temperate regions in search of refuge. In some cases, entire populations went extinct without leaving descendants. The planet seemed to empty itself without anyone noticing. Sea levels began to drop, ocean currents changed, and inland seas retreated, leaving behind salty deserts. Large herbivores became isolated in increasingly arid regions. Air humidity decreased and tropical forests turned into savannas. The ecosystems they depended on were dying slowly. Meanwhile, small mammals and primitive birds thrived quietly. Their size, ability to hide in burrows, and varied diet protected them from the harshest changes. In the approaching chaos, these traits would prove vital. The future would not belong to the giants, but to the discreet survivors of the undergrowth and treetops. The Earth as a whole was undergoing a profound transition. Geological records reveal rapid climate fluctuations, periods of tropical heat followed by abrupt temperature drops. In some areas, vegetation adapted, in others it disappeared entirely. Animals, forced to migrate, generated conflicts over territory and food. Fossil evidence from Montana shows battle marks among large herbivores, as if resources were already too scarce for all. Abundance had given way to competition. Yet the planet still shone with life. Late Cretaceous sunsets were spectacles of color and movement. Birds crossing the orange sky, herbivores moving in endless columns, pterosaurs gliding over golden seas. But beneath this beauty, the ecological balance was exhausted. Seas were losing oxygen. Carbon dioxide was accumulating. The food chain was trembling. Nature, which had reinvented itself countless times, was preparing for one final restructuring. Far from the planet, in the asteroid belt, a 12-kilometer rock slowly rotated in its orbit. A fragment dislodged by a collision millions of years earlier, traveling aimlessly toward the inner solar system. For millions of years, its trajectory was innocent, harmless, until Jupiter's gravity nudged it just a few degrees. That slight deflection changed Earth's history. The celestial body crossed the void for thousands of years, invisible to the world awaiting it. Meanwhile, dinosaurs followed their routines, hunting, migrating, raising their young. Oceans breathed, volcanoes roared, forests flourished. Nothing on the planet hinted that the age of giants was coming to an end. The day of the Chicxulub asteroid. It was a dawn like any other in the late Cretaceous. Over the coasts of what is now the Yucatan Peninsula, the sea shimmered under a warm sun, and the air was teeming with life. Flocks of primitive birds soared across the sky, hadrosaurs drank from rivers, and among the mangroves, small mammals scurried along the damp ground. At more than 30,000 kilometers per hour, a 12-kilometer diameter asteroid approached Earth. It had traveled for millions of years from the asteroid belt, deflected by Jupiter's gravity. In the vacuum of space, its surface burned silently. In the terrestrial sky, it appeared as a second sun, streaking through the atmosphere with a fiery tail that illuminated the entire planet. The impact occurred in an instant, 66 million years ago. The rock struck the Yucatan Peninsula with energy equivalent to more than 10 billion atomic bombs. The shockwave spread in all directions, vaporizing the crust and hurling tons of molten rock into space. At the impact site, a crater nearly 200 kilometers in diameter was formed. Chicxulub. Temperatures briefly reached 25,000 degrees Celsius. Everything within hundreds of kilometers became fire. The sea rose like a wall. A tsunami over 1,000 meters high struck the Caribbean coasts, swept through the Gulf of Mexico, and reached present-day North America. Waves surged inland, flattening forests, plains, and deserts. In minutes, coastal ecosystems vanished. Fossils found in Dakota and New Mexico still preserve marine sediment layers atop terrestrial animal remains. The geological mark of the day, the ocean, rose against the Earth. The energy released by the impact projected millions of incandescent fragments into space, which upon re-entering the atmosphere set the sky ablaze. For hours, the entire planet was a firestorm. Forests burned, nests were consumed, and rivers boiled from accumulated heat. In less than a day, the planet's surface became a plain of ash. Animals that did not die from fire perished from suffocation. Temperatures soared to impossible levels. The air was thick with dust and sulfur dioxide. It was the most devastating natural apocalypse since the birth of complex life. As hours passed, sunlight disappeared. Dust, soot, and sulfate particles blanketed the atmosphere, blocking solar radiation for months. Global temperatures plummeted. Plants ceased photosynthesis, and food chains collapsed one by one. Herbivores, deprived of food, died first, then carnivores followed. In just a few weeks, entire ecosystems that had taken millions of years to build crumbled. The oceans were not spared. The impact altered water chemistry. Sulfuric acid from vaporized rocks mixed with rain, making the seas more acidic. Marine creatures dependent on calcium, like ammonites and corals, literally dissolved. Large marine reptiles, such as mosasaurs and plesiosaurs, perished as prey became scarce. The sea, a source of life for eons, turned into a liquid desert. On land, the scenes were unimaginable. Forests burned for weeks afterward. The sky remained dim, tinged grey and red. Temperatures dropped enough to freeze lakes and rivers. Smaller dinosaurs sought refuge but failed. Most perished from cold or starvation. Only a few survived, those with lightweight bodies, fast metabolisms, and adaptability. Among them were the direct descendants of feathered dinosaurs, birds. Geological evidence indicates that impact dust lingered in the atmosphere for over a year. During that time, the planet endured a global night. Without sufficient light or heat, vegetation nearly vanished. Average temperatures fell more than 10 degrees. Acidic rains destroyed fertile soils. In that dark world, only animals capable of hibernation, burrowing, or long-distance flight managed to endure. Insectivorous mammals and birds able to feed on seeds and carrion became the unwitting heirs of the catastrophe. In the fossil record, the asteroid impact marks a visible line, the KPG boundary, a thin clay layer rich in iridium, an element rare in Earth's crust but abundant in meteorites. This layer, found worldwide, is the silent witness to the day the Earth changed eras. Below it, fossils abound. Above it, traces are scarce. Along this line, non-avian dinosaurs, pterosaurs, large marine reptiles, and 3/4 of all species on the planet perished. The destruction was nearly total, but not absolute. Some regions, especially at the poles and underground, offered temporary refuge. There, small mammals survived by feeding on roots, fungi, and insects. The hardiest birds, direct heirs of the mighty theropods, kept their warmth under feathers and migrated to milder regions. In them, the evolutionary spark of a lineage that had learned to survive any catastrophe persisted. When the dust clouds began to clear, the planet was unrecognizable. Forests had vanished, rivers were dry, and the air still smelled of ash. But amid the debris, life endured. Ferns were the first to reappear, followed by the hardiest flowering plants. Then the small animals emerged from their burrows. In the silence after the cataclysm, the Earth began its reconstruction. The giants had disappeared. The roars, footsteps, and endless herds of the Mesozoic faded forever. In their place, the world was populated by small, silent, and agile creatures. The final chapter, the dinosaurs that survived. As the cataclysmic dust settled, the earth fell silent. Blackened hills, charred forests, and contaminated rivers were all that remained of the world of giants. The air was still thick with ash, the sky remained grey, and the entire planet seemed to hold its breath. But beneath the ground, among roots and stones, a faint pulse beat, the pulse of life, refusing to disappear. Dinosaurs had ruled the earth for over 160 million years, but their reign ended in days. Yet not all were lost. Among the survivors was a discrete lineage, light-bodied, with hollow bones and a fast heart, the birds, the last descendants of the theropods. These small feathered beings, capable of flight and adaptation, were the direct heirs of a line that had begun with creatures like Archaeopteryx. They were not the new masters of the planet, but the bearers of an ancient flame that had survived the fire. The global winter following the impact lasted years. Temperatures plummeted, acid rain devastated the soils, and ecosystems collapsed. Most plant species disappeared, along with the animals that depended on them. But birds survived thanks to their versatility. Some fed on hard seeds that could remain buried for months. Others hunted insects that had endured underground. Their high metabolism, thermal insulation, and flight ability allowed them to escape the harshest conditions. The lineage of modern birds, the neorniths, emerged from that disaster, adapting to a world in reconstruction. Their bodies became smaller, their beaks replaced teeth, and their wings became tools for migration and survival. Within a few million years, birds colonized every available habitat, regenerating forests, deserts, swamps, and coasts. From the shadows of the cataclysm, the sky once again teemed with life. But they were not the only survivors. Crocodiles, ancient descendants of the archosaurs, endured the impact by taking refuge in deep waters and wetlands. Their slow metabolism and ability to hibernate protected them from cold and food scarcity. Sharks, almost unchanged since the Jurassic, continued to dominate the seas, and mammals, small and discreet, emerged as the new protagonists of the planet. Feeding on insects, carrion, and roots, they survived where the giants had perished. The void left by the dinosaurs opened a new chapter in the history of life, the Cenozoic era. In this new world, birds inherited the skies and mammals the land. The forms once feared and monumental became fossils, petrified traces of the past. Yet echoes of the Mesozoic lived on in every sparrow, eagle, and hummingbird. Their light bones, efficient respiration, and survival instincts were direct inheritances from the ancient theropods. Every flap of wings, every migration, every dawn song was a testament that dinosaurs never truly vanished. They merely changed form. Fossil evidence supports this continuity. Birds retain more dinosaur traits than any other modern animal: pneumatic skeletons, Saurischean pelvises, structural feathers, a continuous flow respiratory system, and even the design of their eggs. Genetically, a chicken shares more with a velociraptor than with a crocodile. In a sense, dinosaurs still fly over us every day. During the first millions of years after the impact, life slowly reorganized. Ferns were pioneers, covering devastated soils. Then new flowering plants arose, adapted to changing light and climate. Insects, emerging from their refuges, resumed pollination. Birds, taking advantage of fruits and seeds, became their main allies. A new alliance between flora and fauna reconstructed the biosphere from scratch. Meanwhile, mammals began their silent ascent. With terrestrial dinosaurs extinct, they occupied niches previously denied to them. Some grew into giant herbivores, others became predators. In a few geological eras, the descendants of those tiny survivors would become elephants, lions, cetaceans, and humans. Earth's history had changed hands, but its roots remained in the Mesozoic. The planet's landscape also transformed. Seas receded, mountains rose, and continents assumed their current shapes. In the humid jungles, descendants of flying dinosaurs diversified into thousands of species: running birds, aquatic birds, raptors, tropical birds. Each carried a fragment of the legacy of the vanished titans. Evolution had not erased dinosaurs, it had refined them. Modern scientists have reconstructed this heritage with astonishing precision. In laboratories, bird DNA reveals traces of their reptilian ancestors. In museums, fossils of feathered theropods show how wings were not born for flight, but for protection and display. In stone, time preserves the story of a slow but irreversible metamorphosis, the transformation of the rulers of the earth into lords of the air. The Cretaceous extinction was an end, but also a beginning. Nature knows neither tragedy nor victory, only continuity. Dinosaurs did not disappear. They fragmented into millions of forms still surviving, invisible to the untrained eye. In bird songs, in the flap of wings over water, in the light bones of a sparrow, the memory of that lost world endures. Today, each sunrise repeats the cycle that began millions of years ago. When a bird rises above the earth, it repeats the gesture of its Mesozoic ancestors. When a flock traces its migratory path over the sea, it perpetuates the survival instinct that saved the lineage from fire and darkness.